talk is held by Befi. He's already here, and he is working in cartography. So he's building maps with the help of cameras, but he also likes to, well, repurpose things that he finds useful for other things. And that is also what he will be talking about in this talk here. It's about Wifibroadcast. So he will show you how to convert standard Wi-Fi dongles into digital broadcast transmitters. Give him a warm applause for his talk.
Yeah, thank you very much. Today I would like to present to you my work on modifying Wi-Fi dongles to serve purposes that they are not intended for by the Wi-Fi standard. And one example would be digital broadcast transmitters, but I will also mention some other examples that you could use them for in the way I intended. So coming to the contents, I will start with a motivation, because the obvious question is, why would you even need to change something with Wi-Fi devices? Because we're using them all day, they're working quite well. This is true for the intended applications, but there are a class of applications in which the Wi-Fi standard, well, fails pretty much. And this is what we will be addressing in this talk. Then, after the motivation example, I will show you the basic principle. And building on top of that, I will introduce some improvements that I introduced to make such a broadcast transmission really bulletproof. And finally, I will give you some usage examples to show that it's really easy to use, and also give you some real video footage that has been transmitted using this broadcasting scheme. So, coming to the motivation. So, my personal motivation, and a rather good example of an application for this technique, is if you would want to build a free open source first-person view drone. So, this can be any type of drone. I just depicted here a quadcopter, could be a land-based drone, doesn't matter. The important part is that this drone has a camera attached to it, and it live streams the video down to the operator of the drone, and the operator flies this drone only by looking at this live stream. So there's no direct line of sight to the drone. So reliability is really important here in this application. And I imagine all of you have an idea how you would realize such a system. And actually, on first glance, it's pretty straightforward. Like, you would just add some Wi-Fi hardware to the drone. You would create an access point with this Wi-Fi hardware, and then on the ground you have a laptop and you connect to that access point. Really simple. And then from the drone you would send down the data, video data, simply by UDP packets. And this looks fairly decent, right? It should work. And if you test it at home, and then you will probably notice that it works really well. And then you go outside, start flying, having the time of your life, and suddenly, oops, you lost association. And this means, of course, you as an operator, you're instantly blindfolded. And good luck trying to rescue your drone in that situation. Well, you might think, maybe it's not so bad. Wi-Fi usually automatically reconnects, and this is true. This might help you. Might not help you. So, yeah, good thing about this is you can directly go shopping parts for a second drone, because your first drone will have already crashed by now. So, in summary, association or stateful connection is something you do not really want in this application. And that's a problem of standard Wi-Fi, because standard Wi-Fi usually uses associations. That's another problem I'm coming to right now. So I wrote here that we are using UDP packages, and this seems to be like a smart choice because it's unidirectional, so you just send data from the drone to the ground station and avoid all the hiccups of, let's say, stream-oriented protocols like TCP. So data could queue up, you need to send acknowledgement up to the drone, which is of course not really something you would want to do. So UDP seems to be a good choice. But in fact, it's not, because under the hood, like on a network layer, it seems to be fine, but on a MAC layer of Wi-Fi, there will still be data flowing from the ground to the drone in the form of acknowledgements. So Wi-Fi uses acknowledgements, and so you actually need to acknowledge the package from the drone. And so you have a required upstream from the ground to the drone. And this is obviously something you would not want to have, because then you rely on two links to be working perfectly to just to get the data from the drone down to the operator. And there's another disadvantage of this bidirectionality, which is actually the term of the problem, that is that you ideally want to have asymmetrical setups. So what would you do to increase the range of the setup? You would, for example, install a power amplifier on the drone side, so that the data gets spread further. But with standard Wi-Fi, you would need to have the same power transmitter also on the ground station, which is again pretty pointless. And so bidirectionality is a problem of standard Wi-Fi. There are a couple of other things. So Wi-Fi has some automatic control mechanisms, like, for example, transmission rate control. So if the two devices are, well, at a certain distance, the signal, receive signal strength, of course, drops at the receiver. And this triggers a mechanism that throttles or dials down the transmission data rate on the transmission side. And this happens automatically. This is not under your control. And so imagine you're trying to send a 10 megabits per second video signal, and suddenly the card decides to just switch to 5 megabits per second. Result will be data will queue up on the drone, latency will increase, you'll crash. Same problem. There's also automatic power control, which makes sense in standard Wi-Fi because you want to limit the interference between close-by networks. So you just send with the, let's say, minimum required amount of energy. But since you rely so much here in this application on this link fully working at any time, you do not really want to have that. You want to use always maximum power in that case. And lastly, you have no signal degradation in standard Wi-Fi. So standard Wi-Fi uses CRC checksums, and it just either delivers you packets that have matching checksum or no packets at all. And this is a problem because let's just assume you fly further and further away from the ground station, and at a certain point, the video feed will just stop because CRC checksums will turn bad. And this is actually almost a crash guarantee again, because you have no warning up front. It's just like, and it's off. And actually what you want is, you want to see the transmission errors. So this gives you a good hint that it's maybe time to turn around, and then you still have enough visual feedback to actually control the drone to move around. So signal degradation, again, not possible in standard Wi-Fi. And yeah, this is kind of the motivation for me to kind of flip things upside down a bit. And now we are coming to the basic principle. It's actually quite simple. So, you know, in standard Wi-Fi, you have the device classes, a station, like an access point where you connect to, and the device that connects to this access point. And in Wi-Fi broadcast, The modes in which the devices work have been renamed by me, so they are simply a transmitter and a receiver. And the hardware used for that is just plain standard Wi-Fi dongles, €8 per piece, so it's pretty cheap. And from this, let's say, mode name, you can already infer that it's a truly unidirectional data flow from transmitter to receiver. And these devices work in injection mode, in the transmitter case. So basically, you can send with that mode arbitrarily shaped packages into the air without any association. And the receiver runs in monitor mode, meaning it will pick up every packets that are floating, all the packets that are floating around in the air. And with an appropriate filter on the receiver side, you just get the packets from your transmitter. And this already establishes a very primitive but surprisingly good working link that does not share all the problems of standard Wi-Fi that I mentioned in the previous slide. In theory, this is super easy to do. The APIs for these special modes like injection mode and monitor mode are there already. You can just use them, implement it in a couple of lines, and you should be good to go. In reality, the injection side is quite, let's say, quite a bit more complicated than anticipated, because we're basically leaving here the domain of standardized Wi-Fi and are, well, hacking, fiddling somewhere outside of the standardized domain. And you have no guarantees how the hardware will react in this non-standardized way. So one problem I discovered was low injection rate. Many chipsets I tested really had terrible injection rates, like in some cases in the order of 1% of the air data rate. I could only get through that. So this was pretty bad. I solved this by just selecting good chipsets in a way. Then many of these drivers and firmwares I tested ignored quite crucial parameters I requested them to obey to. So for example, TX power. I found many adapters ignoring this setting and just sending at a low minimal power value, which is of course not what we want. But simple, dirty, and don't look at the actual lines, but it's just a couple of lines. Kernel driver patch fixed that for me. Even more importantly, some devices ignored data rate requests. So I requested to send a packet at, I don't know, 54 megabits per second, and these drivers were always sending the packet at 1 megabit per second, which is not enough for video, for example. Luckily, there is one specific Wi-Fi dongle that I showed in the pictures earlier that has open source firmware. So you can just download that firmware, compile it, flash it onto the Wi-Fi card, and actually, again, to have control over the data rate, it was just a one-line change in the firmware, and I could specify exactly the transmission parameters that I needed for my project. Now, with all the troubles fixed, so to say, we're again back at this basic scheme, and this works already quite well. So if you install this on your drone, there's no problem flying around a couple of 100 meters with such a setup without any special ingredients like amplifiers, big antennas, and so forth. But my initial motivation for this project was more to explore the world from a bird's eye perspective. So a couple of 100 meters didn't really cut it. So I wanted to increase the possible range by any means. And one of these means is to just add more of these cheap dongles on the receiver side. You can just put them in there, and this will then enable you to do software diversity. And at first glance, you might think, well, this looks not really helpful. we have 3 times receivers that receive the same data stream from the receiver, so we will have only 3 copies of the same data at hand. What should we do with that? In reality, this actually helps quite a bit, and the reason for that is that in reality you have multi-pass interference. So starting from this oversimplified transmission scheme, you will never encounter such a transmission here on Earth, maybe in space. But here on Earth, you have other objects that cause reflections of the signal. And these reflections will interfere at the receiver side, either constructively or destructively. And it's simply pure chance whether you will get a constructive or a destructive interference. And by placing several receivers at different locations, you basically can twist a bit the shape of this triangle here. And this basically helps you to get a better chance that at least one of the receivers will not suffer from destructive interference. And actually, in reality, this really helps a lot. There are other use cases of this software diversity. For example, you could use that to realize antenna diversity. So typically, if you look at these black antennas here, these are omnidirectional antennas giving you 360 degrees coverage. And this is already a good starting point, but with antenna diversity, you can add different antennas to different receivers. So for example, you could add to the 360 degrees antenna a very high gain, long range directional antenna. If you know, well, I'm just flying in that direction, long range, you can just combine the antennas depending on your needs. And if you really invest a bit more, you can just use lots of directional long range antennas and realize, well, let's say an antenna that's really not feasible to do with just antenna magic electronic means, so to say. And third use case is, of course, you can increase the spatial coverage. So there are situations like this top-down view scenario where you have occlusions which the transmitted signals cannot pass over. And in that case, you can simply place several receivers at different locations, and the software will automatically fuse the signals from these receivers so that you get, in the end, only one logical data stream out of that, which does all the handover stuff and everything automatically from one stick to another. Let me quickly explain to you how this works. It's quite simple. So we have here an example with 3 cards and 4 packets. These arise, of course, consecutively. And let's just imagine, card 0 received a package with a CRC error. So there's something wrong. We don't know exactly how much. At least 1 bit seems to be flipped, but could be not really severe, could be really severe, we don't know. But the other cards received good packets, so we just pick one of the 2 greens and we're fine and have a good packet here received. Packet 2 might be good on card 0, CRC error on card 1, for example, and it might be completely missing for card 2. So in that case, of course, easy choice, we pick the green one, which is fine, and we have a good packet in the end. Now packet 2 might have a CRC, completely missing, and again a CRC. So what would we do here? Well, it's a tough choice, but the best thing we could do is to pick one of the packets with a CRC error. Maybe preferably the packet with the higher received signal strength. But besides that, there's not much more we could do. And packet 3 might be missing on all of the cards. And this typically happens when you have some external interference, like someone switches on a light, creates a spark, and this destroys the reception on all of your Now taking this combined stream of packets, this is of course not satisfactory. So this is still better than one card, but there are still some artifacts. And how could we deal with these? Well, simply by adding forward error correction to the data. And the way I implemented it is actually quite straightforward. So to these payload data packets, I simply add forward error correction packets, 2 or more. It's configurable depending on your needs and on your link quality. And of course, now for the first 2 packets, there's nothing to be done. They are good already. And now we are dealing with the broken packages. And we start with the worst case, which is the missing packet. We have no data at all here, so we can, or we should start with that one. And so we apply the first FEC packet to the missing packet. And you can think of these FEC packets as, well, joker cards, so to say. So you can recalculate one of the data packets by using this FEC packet. So this one is used up, and from that we could reprocess the original value of this packet. And of course we will then do the same thing with packet 2, and now we have a good data stream again. Of course, this is now the optimal example. In reality, you sometimes have situations where you used up all FEC packets before you repaired all data packets. That can happen. If that happens too often, you should just dial up the number of FEC packages and you should be good again. All right, so this was the basic principle, and now I'd just like to show you some usage examples of the tools that I developed that realizes this transfer mode. So first, a bit artificial example is simple file transfer. So we first start the receiver because we want to capture all packages from the transceiver and not start in the middle, and this simply works by starting this RX program. This is part of the Wifibroadcast software, and you just specify the Wi-Fi adapter that it should use. And in case of software diversity, you would just list several adapters, and it would automatically do the software diversity under the hood. And what this does is basically all the data it receives, it will output on STD out, and you can pipe this into ImageMagic's display program. On the transmitter side, it's the same in verse, so you just output something to STD out file, in this case a GIF file of your new drone, and you pipe that into the TX program of Wifibroadcast. And it's as soon as you execute this command, it will be sent out into the air and picked up by the receiver and subsequently displayed by ImageMagic. So pretty simple, but like I said, artificial setup. This is now an actual example that I'm using, for example, on my drone. So to transmit the video. So as a PC, I'm using a Raspberry Pi, just sitting on the drone, and I start this command. So this looks a bit more complicated, but it's actually fairly simple. So the first part of this, from here to the pipe, is simply a standard Raspberry Pi tool that outputs H.264 compressed video data on STD out. And again, you pipe that into the TX program, and it will immediately be sent out into the air. There's no need to have any receiver enabled. It will just be emitted in the air. There's another alternative. So if you do not want to use a Raspberry Pi, you could simply use a GStreamer API call, which is pretty much the same thing. So you capture from a video for Linux device, compress it to H.264, and then output it to standard output and pipe that into the TX program. On the receiving end, you can do, again, the same in reverse. You use the RX program, pipe that into a GStreamer pipeline, and display that image onto your screen. And this is already a setup that is able to fly for you pretty well. Now, Wifibroadcast is actually agnostic to the data it transports. So it's just you pipe data in and it falls out on the other side of the channel, so to say. And this on its own is not very useful, and therefore I developed some components that kind of complete the drone application. And one thing is, for example, I created a Raspberry Pi image that you can simply burn onto 2 SD cards. You put these into your RX and TX Raspberry Pi and switch them on, and you have a video link running. So that's quite nice. And on the RX side, you have also support for recording. So if you just add a USB stick to the Raspberry Pi, you will automatically record the video of that transmission. I also developed OSD, stands for on-screen display. It's an overlay onto the video that shows some telemetry information of the drone, like battery status and so forth. And I also ported everything to Android. This was a bit more complicated than anticipated. Just to give you some impressions. So this is what you could mount onto your drone, Raspberry Pi Zero, pretty small device, weighs only a couple of grams, and you get the camera already from Raspberry Pi Foundation with it, and yeah, that's a pretty good drone setup that works even on the tiny drones. On the RX side, so this is now my clumsy self-made setup. On the left, you see my video goggles that are cut out of some foam piece. In the middle is the blue thing is the battery, and on the right, the gray box is a Raspberry Pi, and the white thing is, of course, the Wi-Fi receiver. And this is quite a nice setup. So I have the components in the pockets of my jacket, goggles on my head, and this is enough to fly around. This is an example of the OSD display. Here you see basically everything that might help you to safely get your drone back home, like receive signal strength, battery status, artificial horizon, distance to your